Hi, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This is a calculus video where we're going to look at continuity questions. So a reminder about the definition of continuity. Continuity at a point means that the limit of the function at that point is equal to the value of the function at that point. So we could break that down further because we know that the limit has its own definition. So the left-hand limit at a point and the right-hand limit at a point and the point itself must all be the same value. So let's just again visually have a look at what that means. So I'm going to pick a point sort of here. Let's talk about at this point. So you can see that the point itself exists on the function and it's at a value of 2. And along the left-hand limit, we can see that the function is approaching a value of 2. The right-hand limit, it's also approaching a value of 2. So the left-hand limit, the right-hand limit, and the point itself are all approaching the same value. So the function is continuous at this point. And in fact, you can see, as we've discussed, that you're going to find the same thing is true. For every value, every point along this part of the function, the left-hand limit, the right-hand limit, and the point itself are all going to be the same. So the limit exists for all x values within that part of the function. And of course, the arrow means all of the values below that as well. Now, at this point, the graph turns, but you can still see that the left-hand limit approaches 5, the right-hand limit approaches 5, and the point's at 5. So it's still continuous there. And it's going to be continuous this whole part of the function right here. And then we get to this hole. Well, at the hole, yes, the left-hand limit and the right-hand limit are both going to agree, but the function itself isn't there. The function is up here. Or maybe it's nowhere. In this case, it does happen to be somewhere else. But because there's a hole there, then there's definitely not a point where the limit exists. So this is a discontinuity. So it's not continuous at x equals 1. And then as we continue, we can see this is going to be continuous this whole way. And at 5, the left-hand limit and the right-hand limit do not agree. We don't have to check anything else. We know that it's discontinuous at x equals 5. But then it's going to be continuous for this whole thing. So that's why we talk about in class how if you are drawing the function and your pen doesn't have to lift off the page, then you're dealing with continuity. Whereas if you have to lift your pen off the page to put a hole or to put a jump or the other one, which I'll show in a second, then it's discontinuous at that point. So here are the types of discontinuity. So again, we've looked, there's a hole. So at x equals c, there's a hole. That's a discontinuity. It's also called a removable discontinuity. So that's unique, different from the other discontinuities because there is a limit there. The limit would exist there, but not the continuity doesn't exist there. So it's not continuous even though the limit exists at a hole. Then we have a jump discontinuity. So the function suddenly jumps from one y value to another y value. So that is a jump discontinuity. You're going to see that probably only in piecewise functions. And then another possibility that we didn't see in the earlier graph is that you might have a vertical discontinuity, which we call a vertical asymptote if we're visualizing and graphing. And so the limit does not exist at a vertical asymptote. So let's do some continuity questions. Determine if this function is continuous at x equals -1. Explain. Well, that function we know is a polynomial function. And a polynomial function does not have any discontinuities. There's no holes. There's no vertical asymptotes. There's no reason why the function would jump. So therefore, for all x values from -infinity to infinity, a polynomial function is continuous. So at x equals -1, f at x is continuous. And explain continuous. All I need you to say here is that f at x is a polynomial function because we've studied them and we know that polynomial functions are continuous on the entire number line. So we don't have to get into further details. It's a polynomial function. So any x value you give me, we would have continuity at that point. So let's look at another question. So determine if the function, so this time I have a rational function, is continuous at x equals 4. So x equals 4 is where the denominator equals 0. Anywhere else, and this function would be continuous at an x value, because we've studied rational functions. We know that only where the denominator equals 0 is there some sort of interesting thing like a whole or a vertical asymptote. So at x equals 4, I know that the function's discontinuous because having studied rational functions, at x equals 4, there is either a whole or a vertical asymptote. So I know it's not continuous, but let's actually figure out which type of continuity it is, which type of discontinuity it is. So I'm going to factor out the 3 from the numerator, and then I will factor the difference of squares. And I notice that I am able to cancel out the x minus 4 restriction. I mean, the restriction still exists, but this function essentially becomes the linear function 3x plus 12, right? So this would be 3x plus 12 if I wanted to write it that way, but there would be a whole at x equals 4. So f at x is discontinuous. I'll just use a short form at x equals 4. And I could say my explanation, so obviously my algebra part of my explanation, and I could say there is a whole. That's enough. All right, next question. So here I have a piecewise function. So for the function, so there's a function here. There are 2 linear rules, and those rules split at x equals 3. And I want to examine the continuity at x equals 3. So if it was any other value that I asked other than 3 right here, then my answer would be that it's continuous. Because when x is less than 3, the rule is a linear function, which is polynomial and therefore continuous everywhere. But if I were to ask for a number greater than 3, then I would follow this rule, also linear, also polynomial, also continuous everywhere. So it's really only at 3 where the question of continuity is interesting, and of course that's what I've asked you. So let's look at what happens at x equals 3. So we know that we need to examine 3 pieces: the left-hand limit, the right-hand limit, and the function itself. So the left-hand limit is going to be here. So this is where the left-hand limit is going to exist. That's going to be values less than 3. And this part of the domain is going to be the right-hand limit and also the point itself because it's greater than or equal to. Sorry, that's a 3. So we're going to use those rules. So the limit as x approaches 3 from the left of the function. So it follows the function rule 2x minus 5. So I'm able to sub the 3 in because I know what a line looks like. And I know that approaching 3, it would just be approaching, 2.99999 would be the same approach as I'm just going to sub 3 in because it's a limit. So 6 minus 5. So the left-hand limit is 1. And then the right-hand limit as x approaches 3 from the right is also equal to the function itself at 3, which is 3 minus 2, which is 1. So the left-hand limit, the right-hand limit, and the function itself are all equal to 1. And therefore, I can say that the function is f at x is continuous at x equals 3. And of course, I could also say it's continuous for all real numbers, again, because below 3, it's a line which is continuous everywhere. Above 3, it's a different line, but continuous everywhere. And at 3, it's also continuous. So this is a continuous function at x equals 3 and everywhere. Next question. So similar to the last question, I have a piecewise function, and I want to examine the continuity at x equals -2. So what I have is I have a polynomial, a cubic function when x is not equal to 2. So that's both the left-hand limit and the right-hand limit because x not equal to 2 everywhere else. So just below -2, just above -2, I'm going to follow the rule x cubed. At x equals -2, I follow this very different root rule. So let's examine these limits so that we can then talk about continuity. So the left-hand limit, notation. So the left-hand limit as x approaches -2 of the function is the same as the right-hand limit as x approaches -2, which is, so I just need to follow this rule, is -2 cubed, which is -8. Yes, my notation is not great, but I'm trying to squeeze it into your screen. So I know that the left and the right-hand limit are the same, which are -8. And now I'm going to look at the actual function, which follows this rule. So f at -2 is the square root of -2 squared plus 5, which is √9, which is equal to 3. Well, 3 is not equal to -8. So therefore, there must be a jump. Or, yeah, there'd be a jump. What else? Yeah, no, it's just called a jump. There's no special name for jump discontinuity. I always assumed that there would be because jump seems like a casual thing. But, you know, I guess it's the best word there is. So there is a jump discontinuity at x equals -2. The limit exists at x equals -2, but continuity is not held up because the point is somewhere else. So you'd see an open circle. I'm not trying to draw what it actually looks like. You would see an open circle at x equals -2, and the point would be somewhere vertically different from that whole location. All right, one more question, maybe two. So slightly different here. Again, piecewise functions. That's kind of where things get interesting, honestly. So there's a piecewise function. And you'll notice that the second rule has an a value, meaning an unknown constant. And it says for what a value is the function continuous everywhere. So we know that when x is less than 4, we have a linear function. So it's definitely continuous below 4. And then for values greater than 4, we also have a linear function. We just don't know that value, but it's still going to be linear. So we already know that it's continuous everywhere, except for we haven't examined what happens at 4. So we want it to be continuous at 4. So the goal is to make it continuous at 4. So that means we need the left-hand limit, the right-hand limit, and the function itself, the value of the function itself to be the same. So we can look at the left-hand limit first because there's no a here. We can actually calculate exactly what the left-hand limit is. So the limit as x approaches 4 from the left follows the rule x minus 14. So 4 minus 14, it would be -10. So in order for my function to be continuous at this point, I need both the right-hand rule and the function itself to also be -10. So I'm now going to focus on this part of the function rule because that's where the function exists, and it's also where the right-hand limit exists. So what I want is the limit as x approaches 4 from the right and the function itself to be equal to -10. So obviously it's easier to just sort of focus on the function itself because the left-hand limit is part of the same rule. So if I sub 4 in to the function rule, I want the answer to be -10. So f at 4 is a times x, which is 4, plus 2. I need that to be equal to -10 so that there's continuity. So let's look at this algebra. What I have is 4a plus 2 equals -10. Just solve for a. So 4a equals -12 and a equals -3. So if a was -3, so if my function looked like this, so -3x plus 2, then what would happen is at x equals 4, the left-hand limit would be -10. The right-hand limit, well, if I sub 4 in here, I would have -3 times 4, which is -12, plus 2 is -10. And the function itself is the same rule, would be -10. So both the top rule and the bottom rule would give me a value of -10 when I'm testing limits and the function. So I need a to equal -3. any other a value and it would not be continuous there. So I think this is the final question in this video. Similar to the last one, I've got a piecewise function, but there's an unknown value. In this case, the unknown value is where the function rule changes from the first rule to the second. And again, I want to find what a value makes this function continuous everywhere. So below a, I know I have continuity because that is a linear function. Above a, I know I have continuity because that is a constant function. So it's really only at a where I have to worry about the continuity. So I don't know where that break happens, but I do know that the right-hand limit, so the right-hand limit at a is equal to -7. Now that's also the function itself at a, because again, this rule applies to both the right-hand limit and the function. So the output at a following the right-hand limit and the function is -7. Now what that means is that I need the left-hand limit to agree. So I need the left-hand limit at a to also be equal to -7. So let me write that algebraically. I need the left-hand limit to also be equal to -7 in order for continuity to exist. And what is the left-hand limit? Well, that follows this rule, which says 2 times x plus 3. So x is equal to a, because that's where I'm interested. So now I have this little bit of algebra to solve for. So -10 equals 2a, a equals -5. So if a is -5, then my function is continuous everywhere. And again, we can check that. If a is -5, then we know the right-hand limit is -7, the function is -7, and the left-hand limit, if I sub -5 in, I also get -7. So I hope this has been helpful. Please make sure you practice math. Don't just watch me do it. And good luck in your studies.